Alright, good morning guys. I wanted to go over vectors again with you. Alright, so I'm picking up, I did this a little bit in the last video, but I'm going to do it again now. To find the resultant of two vectors, you construct a parallelogram wherein the two vectors are adjacent sides. So this is going to deal with situations in which somebody is hanging from multiple strings that may or may not be parallel to each other. In this case, they are going to be not quite perpendicular. You'll see in some of the examples down the line. Okay, so again, very quick, vectors show magnitude and direction. There's your example. The sum of the two are resultants. I'm going to repeat again. This is very important. So when you do your Cornell notes, we have vectors at the top and resultants here. So it's a sum of two or more vectors. So here we go. 50 going one direction, 100 newtons going one direction, 150. Right? So all kind of review. Basic math, if they're going in the same direction, they add. If they're going in opposite directions, they subtract. Or you could think of this like a number line. When you think your number line has 0 in the center, then these are all your negative numbers, and here are all your positive numbers. Everything going in the positive direction is positive. So if it's going in this direction, it's positive. If it's going in this direction, it's negative, just like they show there. Same situation with up and down. Up is a positive direction, down would be a negative direction. Okay, so this is an easy one. We have this Nellie Newton lady. She's hanging from a string. So since she's not moving, her tension force of tension, is equal and opposite to her force of gravity. Okay, now if you have two ropes, her force of tension is split between the two ropes, but it's still equal and opposite her force of gravity, force of tension. So it's basic math here. If I added a third one, each one would be even shorter. So pardon that one. If I did 3 ropes, they'd have 3 with even less size. Alright? Because she is splitting her weight among 3 ropes. We could go on and on. Make sure the rope is actually attached to the top and to her. Don't get this confused with the flagpole experiment, which has a rope attached to a guy and attached to a flagpole. That's not the same, because all of his weight is being held up by the flagpole instead of split by him and the rope. Okay, so here's some, you're not going to see a lot of situations like this where the tension forces are going up and to the right. It'd be like doing this. Sorry, you can't see me. Which doesn't happen often. It would be more like this, where your arms are split in some sort of V. But we're going to use it in this direction. The vectors are, when they're at right angles, you can use a special rule. They're not always going to be at right angles, but if they're not parallel, we can use the parallelogram rule, which says these two, you can add them, well, you have to use a special case of adding to determine the resultant. So the resultant is between the two. So I think I inaccurately drew this. If you see, the greater force is on the one going to the right, so the resultant should be further to the right. Now if the vector going north or up was bigger, then the resultant would be going closer to that. It would have a narrow or more acute angle going up to the north direction. Now, as long as they're at a right angle, and this only works for right angles, you can solve for the resultant using the Pythagorean theorem. Only for right angles. If they're not right angles, we're not getting into that math this year, so I'm not going to ask you to solve for it. But if it is a right angle, you can use the Pythagorean theorem. A squared plus b squared equals c squared. Okay, where are a, b, and c? What does that mean? Well, pick a side. Pick one of the perpendicular sides. So in this case, oops, camera is backwards. There we go. Pardon me as I figure this out. This side is A, and this side could be B. So And because it's a parallelogram, A and A are equal to each other, B and B are equal to each other, which means the third side of the triangle is C. So, in order to find the result in the third side of the triangle, you would plug in the number for A and the number for B to solve for C. You have to use algebra here. You have to keep things on the right side. Pay attention to your math when you do something like this. And again, only works for right angles. Okay, so here's the situation. This is not necessarily a right angle. They don't give you this, so don't rely on that being a right angle. Okay, like I said, not necessarily a right angle, but you can still use the parallelogram rule. So this, I'm going to show you how this works out when it's not perfectly perpendicular, not a perfect right angle. Okay, so this is saying you take the two sides of tension and you create a parallelogram out of it. Okay, well, how do you figure out where the other side of the parallelogram is? Great question. When you look at Nellie, you look at the force arrow of gravity. Now you build an equal and opposite force arrow going up. Okay. Once you build it going up, that indicates your other corner. Wow, that was a really sloppy arrow. That indicates the other corner of the parallelogram. So now you follow the lines of this. That was not close enough, so you got to get close to the corner of the arrow. And this. So I tried. That was really sloppy, but notice this one should be parallel with this one. This one should be parallel with that one. Okay. Once you do that, that indicates how much force is being, or how much the force of tension is being applied to each side. So you would draw an arrow at this point and at this point. And here are your force arrows. That was really inaccurate because my parallel lines were terrible. So when you have it on a flat surface, use a ruler to make sure your lines are parallel to get a more accurate picture of this. Okay, so here we go again. So there's your downward force, there's the parallel lines. This line and this line are parallel, this line and this line are parallel. And that allows us to determine that the force was really evenly split between those two rows. Okay, now, as the angle increases, the tension is going to increase. Because look at this. So at some point, the tension on the ropes exceeds the tension of her weight. If you measure this, this is only like this big if you think about it. So the wider the ropes go, so think about putting your arms out like this. How hard would it be to hold yourself up like this instead of like this? Very hard. It's a lot more difficult because of the angle of the force that you're applying. So there's a lot more likelihood, because this tension is so great, a lot more likelihood that it's going to break. It's going to be very difficult. So okay, there's other situations. Notice, it makes sense. More force is on the straighter line. You still do your parallelogram. Go back. And you see this has a greater force versus this. Okay? Every time the parallelogram rule works in this situation, you just can't mathematically calculate it. If you can't mathematically calculate a resultant unless it's at a right angle, or unless you're in honors or AP physics when you're learning trig and learning calculus. Okay, so in this case, this shows this example. This rope can easily hold this dude. It's holding it in a straight line. But when you hang on to a clothing line that's stretched across this way, the tension is so much greater, alright, because of the angle that the tension force is being applied. So he has a lot greater likelihood that he's going to break the line, even if he's the same weight or lighter than the guy on the tire swing. Okay, same thing here. There's much less tension here for this guy than this lady, because of the angle of the forces. So that's why you never see swings like that. Alright, I hope this helped clear up vectors. It is not an easy concept, but take your time, work through this, practice some practice questions, and that should help. Right. I'm going to stop here, and I'm going to also post some practice questions. Alright, Consider what would happen if you suspended a 10 Newton object midway along a very tight guitar string. Would it be possible for the string to remain horizontal without slight sag? No. It's the same as a strong man, one in Webb assign. Nearly impossible to hold that up. Alright, the guitar string is always going to sag because of the level of tension that that weight would apply. Alright, I'm going to do another one with the assessment questions for practice. Hope this helped, and have a good night, or have a good day.